All right, good morning. So this is the lecture for Monday, March 16th. This is supposed to be the last lecture for the thermodynamics chapter, chapter 17. And then from there, we're going to be moving on into our, we were supposed to be preparing for exam number 2, but our schedule is going to be a little bit different. We're going to get right into electrochemistry as we kind of move that part forward with our exam being delayed until after spring break, right? And so this first warm-up question is having us talk about entropy. So remember that entropy is the movement towards disorder, right? Or randomness is another way that you can think of it. And so when we're showing a decrease in entropy, it means that we're getting more ordered or more disordered, right? So when we're looking at this option, like for part A, right, you're looking from going from a liquid to a gas, right? Now liquids are more ordered than gases, so that shouldn't be a decrease in entropy, that's actually an increase in entropy. Same thing with our Na plus and our Cl minus as that disassociates, right? We have our particles coming apart, definitely an increase in entropy. N2 and O2 going to nitrogen monoxide, right? We have a mixing there. We have our particles, instead of being N2 and O2 where our oxygens are separate, they're mixed together with our N and our O. You can also think of it as being that there's a stronger bond between the N and the O in nitrogen monoxide than there is between the N2 and the O2 separately. And then when we go to our last one, we're going from 2 moles of gas to 1 mole of gas. And so clearly that is going to be a decrease in our entropy because we went from having 2 objects where things can move around and be rearranged to having just 1. And so our answer is D. This next one, which of the following is true? And now in this several different statements, right? And so what you can do as we go through this is when we get a new question, go ahead and pause it. And you can think about what you're doing. And then you can always play the video again once you're done, because I'm just going to start explaining right away. Right? And so which of the following is true? It's asking us entropy is an extensive property. Entropy is not temperature dependent. Exothermic processes decrease the entropy of the surroundings. Delta S of the universe is always greater than 0 for a non-spontaneous process, or none of the above is true. Now, we are moving forward in that well, our delta S of a universe does generally go up, but that doesn't mean that it's always true for a non-spontaneous process that is greater than 0, right? A non-spontaneous process means that we have to input that energy, and if we have to input that energy, then we can overcome that entropy barrier, right? So as long as we're inputting that entropy to make that true, then our delta S of a universe doesn't always have to be increasing. And so D is definitely not always correct. Right? It would be more correct with a spontaneous process, right? Exothermic processes decrease the entropy of the surroundings, while exothermic processes release heat. Heat increases the entropy. So that's not true as well. Entropy is definitely temperature dependent, right? The different temperatures that you have, whether you're colder where you have less energy and less movement versus when you're hotter and you have more movement, does change our entropy process. So the last one is that entropy is an extensive process, which is our answer. Entropy is an extensive process because as we change the amount of material going through that process, we gain or release more entropy. So which of the following is always spontaneous? Now, when it's asking us which of the following is always spontaneous, it's really asking us to do a comparison. It wants us to look for our delta H and our delta S and how we would compare them. So our delta H and our delta S. All right. Now, when we're looking for an always spontaneous process, that means that our delta H should be negative, right? It should be an exothermic process, and we should be increasing our entropy. That's what's ideal for both of them. So we're looking at that top one. We definitely have a delta H, which is less than 0 because they told us that. Right? And then we know that we have a delta S that is going to be positive. It's increasing. We're going from a liquid to a gas. It's looking like it's going to be A already. Right? But we can look at our other ones. A sublimation of dry ice. That's definitely a positive delta S. Freezing of water. that is definitely a negative delta S as it goes from being a liquid to a solid. Formation of water from its gaseous element. So that's H2 plus O2 going to H2O. So we have 3 moles of gas going to, once we balance this, 2 moles of water. It doesn't seem like delta S is going to be positive. And so looking at this, we know that this one has negative delta H and the positive delta S. So that's definitely going to be our answer, right? This sublimation of dry ice, delta S is positive, but when it sublimes, it's not losing energy, right? We're not gaining energy as it goes, or not energy, enthalpy. It's not an exothermic process for that, right? We actually gain, we go through the exothermic process when we go from the gas to the solid, when we do the fusion, as it forms those stronger bonds, right? And so for this one, we're looking for A as our answer. So that's our warm-up. So just remember that as you're working through these, it's important to practice the concepts, right? And while it's harder for me to check in to see where, how you're doing with them, if you ever have questions about the warm-ups, just let me know, and we can always go through those in more detail with you. And so by now, we should be able to calculate our Gibbs free energy, right? Now, we've been doing this in a couple of different ways, and one of them is that we can just add up the Gibbs free energy for formations for their products and their reactants. Right? At temperatures other than 25 degrees, then we can also find that by using their delta H's, their enthalpies, and their entropies, as long as we use this reaction down here below, right? Delta H reaction minus T delta S for that reaction. Or we can do it like Hess's law, where we can take that reaction and we can break it down into different parts. And with the different parts, we can determine the Gibbs free energy. So just remember that when it's got that little F naught sign, right, that's our free energy of formation. And so it's the change of 1 mole of a compound forms from its constituent elements in their standard states. And you would find this the same way you would find enthalpy or you would find entropy. There's generally an appendix that has them all listed in the back. This is given in kilojoules per mole. And the free energy of formation of pure elements in their standard state is 0. So just like how the enthalpy of formation for the pure elements is 0, so is their free energy as we find them. So all of these things hold true because our Gibbs free energy is a state function, which means that it doesn't matter which pathway you choose, whether it's breaking it down into other different reactions, whether it's going from their standard heats of formations and entropy of formations, or if it's from their Gibbs free energies of formations, those things are all going to be the same delta G value at the end. But it is an extensive process, so it doesn't matter which direction the process goes. If a reaction is reversed, then the sign of its delta G is inverse. The amount, or not inverse, reversed. The amount of material does change things. So if we multiply a delta G by a factor, then the value of the delta G is multiplied by the same factor, right? So if we do 2 times that reaction, then its delta G is also got to go up 2 times. Right? And so we have some practice ones with this. So go ahead, take a moment, practice through, and then let's see how we do. Right? So we know that our delta G of our reaction, given above, is 32.96 kilojoules per mole. Now, when we compare that to our reaction down here, right, we can see that our NH3 has moved across, which means that our delta G is definitely going to be flipped here, make it a positive. We can also see that this value, our 2 compared to the 4, needs this to be doubled by 2. So we take 32.96, and we double it by 2, we should be getting B 65.92 as we move forward. And so on Tuesday, or last Thursday, I guess, last Wednesday, we talked about that free energy. It gets its name because this is the energy that's available for it to do this work, right? For it to go out and be released from a system to the surroundings. And so it can do that either by the entropy change or by the enthalpy change. And so this is going to tell us whether something is spontaneous or not, right? Because we can get a mixture of different things at different temperatures, and sometimes those be spontaneous, sometimes they won't be spontaneous at all. Sometimes they can be spontaneous at low temperature or only spontaneous at higher temperatures, right? And so it depends. So Gibbs free energy, delta G, kind of gives us a check for that. And it has us look at, well, does the enthalpy drive this process or does the entropy drive this process, right? So when we look at this one, this delta H is an exothermic process, right? Which is going to be favorable in that it's going to prefer to go to the product side. The delta S is unfavorable because it's a negative change, right? But what we can see is that this temperature, 25 degrees Celsius, because they have the little knot signs up here, that the delta G is a -1, and so that means that it is spontaneous, right? If it was at 0, it would mean it was at equilibrium, and the positive is a non-spontaneous one. And so we know that delta G is less, and so then we are releasing heat energy to the surroundings, and we're increasing the entropy of the surroundings, right? And so that means that our process is spontaneous, and it means that this is enthalpy driven. And that's what's driving that process towards its spontaneity, compared to something where our delta S might be the positive one, being the one driving the process forward. Now, the free energy is the theoretical limit, right? This is the most that we could possibly get done from our reversible or irreversible reaction, right? If the reaction ever achieves its theoretical limit, once it's given off all that energy, then it moves to become a reversible reaction because it's at our equilibrium, right? So it's basically slowly moving and giving away all of the energy that it possibly can to do all of that work, right? So like here down at the bottom, this gas, right, can slowly expand, right? And when it gets to a certain point, then the amount of sand on the top is just enough to match the pressure of the gas, right? And that's kind of what free energy is doing, is our free energy will go through this process. It might release energy until it can no longer release, until it's at that theoretical limit. And at that point, it's going to become a reversible reaction. Now, in a real reaction, most, if not, or some, if not most of the free energy is lost as heat, right? That means that as you go through that process, as we transfer energy inside of our bonds, we give out a lot of enthalpy, right? There's a lot of heat reaction that goes through. And so when we lose that heat, it goes out into our surroundings, and then from there into the universe. And so since we're using all that heat, our real reactions are generally irreversible, because instead of this visual where that energy stays within the gaseous system and slowly comes to a balance, in the real reaction, once we lose that energy going out, holding up that sand, we'll lose that heat to the container. That container will lose its heat to the air. That air will lose its heat to more air, right? And so we will basically eventually lose that energy, that heat energy, out past the system and never recover, right? And it's never going to become a reversible system as we go through it. And so that's why we don't always have a continuous process with our heat and our work, because our heat can leave the system. Well, we will always lose some of that heat when we're engaged in a real reaction. So far, we've been looking for our delta G's at standard conditions, right? And so that means that it has that not sign. Now, at standard conditions, this was their normal state of that temperature. The partial pressure of the gas was 1 atms, and then the concentration was 1 molarity. This is only true for our delta G without the not sign when those things are the same. At non-standard ones, this is the equation. that connects them. Right? And so really what we're doing is we're saying, well, at equilibrium, right, we had this certain condition, right, our standard condition, and we need to adjust that. We need to adjust that by our gas constant, R, and now with your gas constant, you probably don't want to use the liters, atmospheres, kmol. We want to use the joules, mole, Kelvin, the 8.314. We have our temperature, and as usual, temperature is going to be in Kelvin. And then we have our Q, right? Now this Q is the same Q that we've been using throughout the last month or so. I'm not sure how I did that. Let me erase that. Bam. There we go. And so this Q is our reaction quotient. So that means that at our non-standard conditions, if we look at those changes in the concentrations, just like we're setting up our equilibrium expression, we can see how things impact our standard conditions with our change, right? So if we have more product than we should, then we're going to make this right-hand term bigger. Our delta G will become more positive. If we have less product than usual, then our Q becomes smaller, right? And then we see a smaller change in that delta G. Now we know that at equilibrium, delta G is equal to 0. So if we set this as 0 is equal to delta G naught plus RT ln Q, we can see that delta G is equal to negative RT ln Q, and Q is equal to K at equilibrium. And so this is how we get this second equation down here. Now, if they were to give you an equilibrium constant, we should be able to find the delta G naught at a given temperature using just our equilibrium constant. Or if we know where something's going to be at equilibrium, we should be able to find our K expression. Very good. And so this is kind of a visual diagram of that process, right? When our Q is equal to 0, it means that we're very reactant heavy, which means that we need to shift towards making our process. And so if we need to move forward, then our delta G is going to be on the negative side. When we get to equilibrium, our free energy is going to be equal to 0, right? Because we're at that balancing point when our Q is equal to our K. And then when our Q is big, right, that means we're on our product side. That means that we're favoring our products over our reactants. And so our delta G is going to be positive as it moves back in the opposite direction towards our K. And so this is like a diagram about how that relationship works between them, right? If we're reactant heavy, we got to move forward, and so we're getting a negative delta G. If we're product heavy, then we got to be positive. We got to be moving back in the other direction. And so this is our process of how our equilibrium expression and our delta G's are related about whether we're going to be spontaneous or non-spontaneous for a forward process. Now, our K is a little bit different, right? We have our expression for K, our negative RT ln K. And so what this tells us is that our delta G naught has some relationship to that K, right? And so when delta G naught is positive, the reaction is going to be spontaneous in the reverse direction. And we can see that this is going to be positive when K is going to be less than 1. Right? When K is less than 1, the natural log of it goes negative. Right? And then the negative times the negative will give us a positive. Right? So if we take the natural log of something like 0.5, it becomes negative 0.693. And you can see how that would make it a positive delta G. On the other hand, if we take something like the natural log of 1.5, that's a positive 0.405, which then gives us a negative delta G. So our K value gives us an idea about whether things are going to be spontaneous or not in a forward direction under standard conditions. And you can kind of think that a K value tells us whether we favor products or reactants, right? When the K value is equal to 1, it means that we have an equal amount of our reactants and our products. And so our system shouldn't need to move forward one way or the other. Right? When our K is greater than 1, it means that we favor our products, and so we should be moving towards that. And the difference between this and our equilibrium constant expression that we normally have is that when we're doing our expression, we're comparing them when they all started off with the same concentration, 1 molarity or 1 mole, 1 ATM. So if all of them are at the same concentration, we can tell the difference in their K about which way it's going to go forward. Right? And it's because they start off at the same concentration. Right? Whereas in a lot of our equilibrium problems, things might not have started at the same concentration. And so then we would compare our Q versus our K to figure out which way our direction should have to go. So which of the following is true, right? Just like what we had talked about. Well, we know that delta G naught for a reaction is, well, we can look at the top part. We know that delta G naught, if it's positive, then we should be favoring the reverse reaction. And so that means that we shouldn't be favoring moving towards product. We should be moving towards reactant. So that should be our K is less than 1 for it to be positive. And so it looks like these two parts are not going to be correct. They're going with the wrong statement. K less than 1 should be where our delta G naught for our reaction is positive. And K greater than 1 should be when delta G naught is negative. And then as we move from there to our next one, our next one is going to be where we have our delta G and we're trying to look for it at equilibrium. So we know that it is going to be 0 at equilibrium. Now the question is whether that's our delta G naught or a delta G. Now our delta G naught doesn't change. That's all temperature dependent. So when we look at it, our expression delta G is delta G naught plus RT ln Q. When we're getting to equilibrium, we didn't set our delta G naught equal to 0. We set our delta G to 0. Because this is the one that once our equilibrium constant, or sorry, once our reaction quotient, once our concentrations got to their equilibrium, it's this value that goes to 0. Okay? Once everything's at K, then that just gives us our delta G naught, but it doesn't necessarily gives it set that value equal to 0. Okay? And so our delta G is 0 for the delta G of the reaction, not for the delta G naught of the reaction. Let's practice another one, right? We are looking for the delta G naught given an equilibrium constant of 1.32 times 10 to the third, which means that we need to go backwards, right? We need to take our delta G naught, or sorry, we need to find the expression that connects our delta G naught with our K, and we can move backwards from there. So we're definitely looking for delta G of naught for our reaction is equal to the negative RT ln K. So we're looking for this expression right here. We have our R, 8.314 joules per mole Kelvin. We have our temperature in Kelvin. And then we have our K, So we just need to plug that in. We find the ln of 1.32 times 10 to the third. We multiply it by our 2.479 kilojoules per mole. And you can see here, I've gone ahead and I've changed the unit to kilojoules because all of our answers are in kilojoules. Right? You could have kept in joules first and then changed it at the end, but you do need to adjust that. And so with our positive K, we are looking for a negative, or we should be looking for a negative delta G. And so now I realize that I have a mistake on mine. Right? So the natural log of 1.32 times 10 to the third divided by negative 2.479, or not divided by, multiplied by, gives us a negative 17.8. And so it shouldn't be this one, it should be this one. I can go ahead and I'll highlight that as well. And that should be our correct answer. And that's why it's important sometimes to just do a quick check, right? If I look at my K and my K is positive, then I should have known that my delta G naught was negative. And so I should have known right away that my answer shouldn't have been D. It should definitely have been C. So we're doing that. Moving forward to the next one. Does this reaction favor the formation of reactants or products? So we're looking at our delta G. And so if you wanted to think about it, our delta G naught is related to the negative of our ln K. So that means that our delta G right now is positive. A positive doesn't favor products, right? If it was positive, that means that it's not going to be spontaneous, and so it's not going to favor our forward reaction. Right? So that means that because a positive delta G is going to give us a K that is less than 1, because we need our ln K to be negative, and so our K less than 1. So we need this value to be negative once we do our ln of our K. So our K has to be less than 1. So we're going to favor our reactants because our K is less than 1. And so you just want to kind of practice going through those, changing your equilibrium constants to your delta G's back to equilibrium constants, practicing remembering whether you favor reactants or products based on the equilibrium constants, and then you can look at when your value is that cuts off. Now remember that your 1 value is the important one for our K and our Q's, because the natural log of 1 is 0. Anything less than that becomes negative. Anything more than that goes positive. And so that's why everything is set up equal to your K is equal to your 1 or your Q is equal to your 1. Now, they ask us, why is the equilibrium constant temperature dependent? Right? And so we know we have 2 expressions. We know that we have delta G naught is equal to the enthalpy minus T delta S, right? Our temperature times our entropy. And we know that delta G naught is equal to a negative RT ln K. And so when we put those together, we can get an expression that looks something like this. Negative RT ln K is equal to delta H naught minus T delta S. Now, they want to separate out our ln of our K, so our equilibrium constant. So we have to take these and divide them by our R's. So delta H naught over R. This temperature. Now our entropy, it already had a temperature in it, so we just need to divide that side by R. And if you look at this, they're saying that that expression looks like y equals mx plus b, right? So we have our M, we have our B, and then the 1 over our temperature could be our X. When you plot this out, what you find is that it's generally in a straight line against the inverse of the temperature. Right? And so it would have this slope and this intercept. Right? So once we have a graph and we have that straight line, we can always go back and find the delta H or the delta S by plotting it, by looking for its intercept, by looking for its slope. And so that's one way to connect those two things together. And it all comes because we know these two things are true. So when we put them together, we can see that relationship between them. And so right now it wants to know what is the value of delta G given in equilibrium. Oh no, we already did this one, right? And so I should update that. We can get rid of that one. This is the one that I meant for us to be doing. For the reaction, our entropy is equal to 133.6 joules per mole Kelvin, and our delta H is equal to 131.3 kilojoules per mole. And 298, what we're trying to look for is that temperature is greater than what? This reaction is going to become spontaneous. Right? And so we have our expression. We have delta G naught is delta H naught minus T delta S. Right? Now we know if we find it when delta G is 0, this is going to be when it's at equilibrium. Anything higher than that is going to make it spontaneous, right? Depending on our delta S term. Right? And so we know that this is positive 131.3 kilojoules per mole. And this one, I'm going to go ahead and change it into kilojoules per mole as well. So we can see that as our temperature goes up, this term is going to dominate more. It's going to eventually drive us negative. And so we know that any temperature that's above what we find is going to be when we're going to be spontaneous. So we take that 131. We set that equal to T over 0.1336. We find that our T is 98.2 Kelvin. So we're looking for our E. Another one, we're looking at the free energy of the Haber process. So ammonia is synthesized at, just realize this. Let me see if I can move this one. There we go. Sorry about that. I did not realize that was down this whole time. I hope it wasn't blocking too much. Right? The Haber process, ammonia synthesized from N2 and H2. We get N2 plus 3 H2 grams goes to 2 ammonia. Right? So at 298, the delta G for this is 3.3. The value of delta G for reaction that consists of 1.9, 1.6, and 0.65 is what? And so now we're trying to find out a delta G. So that's going to be under our non-standard conditions. So if it's under non-standard conditions, right? So it should be a delta G naught plus RT ln, and then we should be using our Q because our Q is when we're at non-standard conditions. So we know that this should be negative 33.3 kilojoules per mole plus R 8.3. Oh, not going to have enough space over there. All right. Let us swap over to a whiteboard. All right. So let's see. Yeah. Okay. So we have our expression N2 plus 3 H2s going to our 2 NH3. We know that our expression is delta G is equal to delta G naught plus RT ln Q. We know that our delta G naught is negative kilojoules. We know our R is 8.314 joules mole Kelvin. We know our temperature is 298 Kelvin. So now we just need to find what our Q is. Let me go ahead and erase this a little bit. So our Q should be our products minus our reactants. So our Q should be our equilibrium expression, jumping ahead. We'll make this a little bit. We're going to be our NH3 concentration, or pressure, I guess. Squared, right, our products, divided by our reactants. So we have pressure of N2, pressure of H2Q. So this becomes 0.65 squared over 1.9 Q, right? And so now we just need to plug that in for our Q. So our Q becomes 0.65 squared divided by 1.9 divided by 1.6, 1.6 again, 1.6 one more time, and our Q has become 0.05429. So we plug that in into this part. Now we need to take its ln. We need to multiply that by 298 and by 8.314. And we get something like a negative 7.218. Now the important part is we have to pay attention to our units. So we are going to be in joules per mole. And then this is negative 33.3 kilojoules per mole. That's going to be equal to our delta G. So we got to divide that by 1,000 to get it into kilojoules. And so we find our delta G is being a negative 26.08 kilojoules per mole. Oh, not 28, I'm sorry, negative 40.5 kilojoules per mole. I forgot to add the negative sign in front of my 33.3, right? Which doesn't make any sense because we should be getting more negative. Right? And so now if we jump back to our PowerPoint, we can see that we should be our negative 40.5. Right? If we jump back to our PowerPoint, there we go. It should be our negative 40.5. That's our one for that one. Right? You can kind of see all the work pop up right over there. And then I'll go ahead and erase that for now. Okay. And so then we have a couple conceptual questions, right? The reaction of AF going to BG. There should be an arrow. has an equilibrium constant that is delta G for, all right, I see. My slide has kind of deteriorated here as I transferred it over. Right? So what this should say is the reaction A going to B has an equilibrium constant that is so this one. So it has an equilibrium constant that is less than 1. What can you conclude about the delta G for the reaction? So sorry, for whatever reason, when I copied and pasted this slide over, it's moved them all around, right? So the reaction A going to B has an equilibrium constant that is delta G naught for that reaction. So the reaction A going to B has an equilibrium constant that is less than 1. What can you conclude about delta G naught of the reaction? And so far, K is less than 1. Then we know that we're favoring the reactants. If K is less than 1, then our delta G naught is going to be a positive 1. It's going to be greater than 0. It's going to be a positive. Now, the rest of the slide pack, we've basically covered all of the new material. The rest is just us practicing, right? And so we can walk through some of those. I've also tried to get the examples from the book that have like more detailed responses written out, so that way you guys can get a little bit more support in that way. Right? And so what I would recommend that you do for these is definitely go through them, stop a moment, and then go through the answer, right? And I'll try to go through and elaborate when I can, right? So for this one, we're like looking at this reaction of propane gas. So this is the combustion of propane, like what you do when you like barbecue and you burn a propane tank, right? So we're going to calculate the entropy change in this surroundings when this reaction occurs at 25 degrees Celsius, right? And we're going to use our enthalpy in order to help us take care of that. We're going to determine the sign of the entropy change for the system. And then we're going to determine the sign of the entropy change for the universe. So we're going to determine if it's spontaneous or not. So when it's calculating the entropy change, right, of the surroundings, then we're using our equation, right, our delta H of our reaction is equal to T delta S of our surroundings, but negative, because whatever energy we release from our system, then that's going to be the opposite of what we get in the surroundings. Now that is a terrible handwriting. Let me try that again. Then let's go ahead and let's move on to, let's use this nice purple, right? So our delta H of our reaction is going to be the negative T delta S of our surroundings, right? As we release that heat, it's going out to the surroundings. So when we want to get that set up, we have that rearranged into here, this expression here. We do need to get into Kelvin first. We can take that, we can divide that by our kilojoules per mole, change that into joules, and we can find out what our entropy change is going to be. Right? And so us releasing that heat has really increased the entropy of our surroundings. From there, it wants us to determine the sign of the entropy change for the system. And so we're looking at our system. And so our system was gases on both sides, so we don't have to worry about that as being a source of our change. And so then our next one is we're looking for moles of gases. So we have 6 moles of gases as our reactants, 7 as our products. So our delta S is definitely increasing because we have more moles of gas. And so if we look at this, the last one is it's saying, well, what's the entropy change of the universe? Is the reaction spontaneous? And so it's asking us, is our delta G negative? Now we know what our delta H is, right? And we don't know what our delta S is yet, but we do know that if delta H is negative, and delta S is positive, is there ever a situation where we're not going to be a spontaneous reaction? And the answer is no, right? Because our delta S is always positive, we're always increasing the entropy. And our delta H is always negative, so that's also always increasing the entropy of our surroundings. Then our delta S of our universe is always going to be positive, and the reaction is always going to be spontaneous. So remember that delta S of the universe is really about spontaneity. Yeah? That's what they're asking you when they want you to talk about that. Go ahead and erase that. And so then there's another one that you guys can practice down here as well. All right. And so now we'll look at our next question. Consider the reaction for the decomposition of carbon tetrachloride gas. And then they give us a delta H for a reaction and a delta S for the reaction. They want us to calculate the delta G at 25 degrees Celsius and determine whether it's spontaneous or not. And then if it's not spontaneous, they want to know at what temperature, if any, will it become. And so when it's giving us something like this, we want to think, well, a delta G of our reaction is our delta H minus T delta S. And then we can go from there. So we change over our 25 degrees into Kelvin. And then we just need to plug in our values. So we have our delta H here. We have our delta S right over here. We get them both into joules. And so we get a delta G that's here. Now that delta G is positive. And so a positive one doesn't favor the production of products. And so we're not going to be a spontaneous process, right? We're going to be, we're going to need energy in order to drive this process forward. And that's because our enthalpy requires energy, and our entropy, we're not at a high enough temperature to make that happen. And so since we're not spontaneous, then we have to do part B. We have to figure out, well, at what temperature could we become spontaneous? And if we look at this, our delta H is positive, and our delta S is positive. So that means that this is a positive value, and that this is a minus a temperature, right? Now, as that temperature increases, this term will become more and more negative. And so it's going to go up, or I guess not go up, but go more and more negative. So you can imagine it going down. And eventually it could overcome the positive of our enthalpy, because our enthalpy doesn't change at different temperatures. And so we can set that equal to 0, right? That's our spontaneous one. And we know that any temperature, so this is when we would be at equilibrium. And so we know that any temperature higher than that, when T is greater than, we're going to be spontaneous. We have our delta H in joules. We have our delta S in joules per Kelvin. And we go through and we solve that, and then we get a temperature of 673 Kelvin. And so then if you want another practice one, there's one like that below. And the next one that we have is going to be the delta S of a reaction for the balanced chemical equation. Right? Now, before you begin with this one, you do need to use your appendix. You need to use your appendix to look up the delta S of formations for each of these reactants. So we're going to do this in a slightly different way. Right? We're going to get our chart, and then we're going to work through that part. Now, if you want, we have our chart down here, right? And you can see that we have delta S values for it. Now remember that delta S is always your products minus your reactants. So we need to add up 6 times that of water, 4 times that of nitrogen monoxide, right? So that's what's going on here. We needed 4 of our ammonia and 5 of our O2, our reactants. And then we can subtract them, and we can find our delta S. And so we can check it. We know that it's positive, and it's positive because we are making, if we go back, we're making more moles of gas than we started off with, so we did expect it to be positive. And so then there's another practice one, right? So you still need to use your appendix to recalculate that one. Now on your quiz or your exam, I would give you those values, but it's always good to practice looking up through the appendix. That is a good, useful skill to have, right? So that way you can find your delta H's and your delta S. One of the possible initial steps in the reaction for formation of acidic rain is the oxidation of SO2 to SO3 by this reaction. And so they want us to calculate the delta G and determine whether the reaction is spontaneous. Now, anytime when they don't give us any other information and they just want us to determine it from the reaction, we're back at the appendix. And so for this one, we are going to be looking at our delta H of our reaction. We're going to look for our delta S of our reaction. And we're going to use those to find our delta G by doing our delta H minus T delta S. So we know that our delta HF, right, is below and our delta S. And so we can find our delta H of our reaction by products minus reaction. So this is our delta H of our reaction. We can do the same thing for our delta S. We find that one up here. Then when we plug it in, we just need to make sure that we line up the units, joules to joules. And so the reaction is going to be spontaneous at this given temperature. And it has a value of negative 70.9 kilojoules. You can try it again. Nitrogen monoxide going to nitrogen dioxide. You guys have that one as well. Right. And so for this one, it's the reaction in example 19.6. Estimate the value of delta G at 125 degrees Celsius. Is the reaction more or less spontaneous at this elevated temperature? That is the value of delta G for a reaction more negative or more positive? So example 19.6 was the one that we just did, right? And so we're looking at that value that we have from that. And we're going to find its value at 125. So we have that delta H from before. And we have its delta S from before. Now the difference is that we're going to just try to find what would happen when we change its temperature. So we have gone up in our temperature. We've gone to 125, which means that that T term, right, that delta G equals negative delta H minus T delta S. That T term has become more and more negative because our entropy was negative. Sorry, I'm going to clean up my reaction down here. Yeah. And so we expect this to becoming a more, not quite as spontaneous process, right? So there's a chance that we would flip this over. And so now we have to plug it in. So we find our new temperature, 398 Kelvin. We plug that back in and we get negative 61.5. And so while it's still negative, it's still going to be spontaneous. It is less negative than it was at 25 degrees. So it's not quite as spontaneous as it was before. Mm-hmm. And so then what you can try to do is find out when it becomes not spontaneous any longer, or you can go back and you can look for if we kind of adjust that value to be negative 70.9 at 55 degrees Celsius. They want you to go back and then look at if it's more spontaneous or less spontaneous at the lower temperature. So they want you to basically calculate the value at negative 55 degrees Celsius instead of the 125. So ozone is the lower atmosphere of a pollutant, right? That can form by the following reaction with the unoxidized burning of our hydrocarbons, or in the oxidation of unburned hydrocarbons, right? And so they want us to use the standard ones for this reaction. So this is a big hint that we're going to use our appendix, right? We're going to use some values in order to break that down. So we have in the back several delta G's. Right? Now, if they don't tell you to use the free energies, you could have also been using the free energies for your other reactions as well. But it's important that you practice both ways. So you could go back and you can use your delta H's for this part. You can also use your free energies, for example, as 19.6 and 19.7, right? It doesn't matter, they're going to get us the same place. Right? But just know that if I only give you your enthalpies and your entropies, then that's what we should be using as we go through, right? If you get your free energies, then we need to be using that. And so our free energies work the same way as our enthalpies work. And so if we look for our delta G of our reaction, we're looking for our delta GEFs of our products minus the delta G's of our reactants. And so we plug those in, make sure that we scale them based on how many we have, right? There's 2 of those, there's 8 of those, there's 4 of those. And we should get our enthalpy or our free energy information. Right? There's definitely some more practice ones for this. This is something that I'm not spending too much time on because it's very similar to what you guys have done with thermochemistry. So I'm assuming that you guys are familiar with that, right? But it is something that you want to make sure that you practice. And it's just about remembering products minus reactants, scale them, right? So that way you're using the same ones. Now, this is Hess's law, right? And so it gives us 3 different reactions here, right? So we are looking for this one overall reaction. That's our big one up there, right? But we're going to use these 3 reactions down here at the bottom to kind of set that up. So what you want to do is you want to spend some time and you want to try to arrange them so that these equations look like that. Now, what I would say is look for what's unique. This C3H8 is unique. We're going to turn this into a highlighter. This C3H8 is unique. And so if we're looking for something unique, we're looking in here, and the only one that we have is this is the only one that also has C3H8. Now, why that's important is it lets me know that that reaction is going to have to be flipped, right? And so we'll do that in a second. My solid carbon is only in that one reaction, and we need 3 of them. And my H2 gas is also only in that one reaction. So now I can use that to go through and kind of look at our changes. So this one I know I need a flip. So I need to make this sign a positive one. Oh, it didn't work out as I hoped. I gotta make that one a positive one because we need our C3H8 to be a product. This one down here, we need to multiply it by 3 because I need 3 of those carbons. And this one down here, we need to multiply by 2 because I need 4 of those hydrogens. And so then when we set all of that up, we get something like 3 CO2 gas plus 4 H2O gas going to C3H8 plus 5 O2 gas. We get 3 carbons and 3 oxygens going to 3 CO2. And we get 4 H2, 2 O2 going to 4 H2O. And so then if we start slashing through on those, we see our CO2 here, we see our CO2 here. We have our O2, 3, 4, 5 of our O2. We have our waters, we have our waters. And so we just end up with 3 carbons as a solid plus 4 hydrogens as a gas goes to C3H8. It's a gas, which is exactly what we were looking for. And then they do the same thing down here. You can see how they start to set it up. Right? They work through, they do the same slashes. And so now that they've updated their values right over here, now that they've updated their values over here, they can find the new delta G. So the delta G for this reaction is going to be 23 Kelvin, kilojoules. Okay. So you can try another one where they give you this one down here. All right, we just have a couple more questions. We got one more where we're looking at the delta G under non-standard conditions. And so they've given us our delta G naught for our reaction. That's up here. They've also given us our pressures. And so we should be able to plug that into our delta G is delta G naught plus RT. And they didn't say anything about this being at equilibrium, so this should be our ln Q. Right? Remember that our Q for this expression should be our products over our reactants. So we plug that in. We can find our ln of our Q. We want to make sure that we change our delta G into joules. And then at the end, we can turn it back into kilojoules. So we get our value down there. Now, we know that this is going to be less spontaneous because it's not as negative. It's less negative than our delta G naught. So as we increase our, because we're not at 1 atmosphere of each, we've definitely changed away from being as spontaneous as we used to be. Right. There's another practice one here that you can also work your way through. And then there's one last reaction. So this one, it says use the tabulated free energies of formation to calculate the equilibrium constant. Right? So that means that they want us to go back to our appendix and find our delta G. Right? So we got our appendix down here. And so we use our products minus our reactants, we find our delta G. And so now they want us to find our equilibrium constant. And so we want to remember that delta G naught is negative RT ln K. Now our temperature, because we have that naught sign, should all be at 298 Kelvin. So we can put in this as 2.8 kilojoules is equal to negative 8.314. And that's in joules. Oh. This should be our 298 Kelvin. And then we'll look for ln K. Now just make sure that we line up our units, our joules and our kilojoules, right? Make sure we line those up together. And it basically becomes this expression right here. And we can find our K as being equal to 0.32. And so there's another one to follow up with that. So I hope that this helps. I will try to tighten things up as we move forward, but I wanted to make sure that we at least get this one out. If you have any comments or questions, if there would be some ways that I can make it so you guys can see it better, things like that, then let me know. And then I'll try to get this up for you guys as soon as possible. Have a good one, and don't forget to get started on your thermal chemistry worksheets.